Okay, still okay with the homework? We do our homework? We'll go ahead and start the next section then. I think it's what, 9.3? In this section, we're going to take a look at some special substitutions. We've already done substitutions before, but this is different. It's a trig substitution. You'll notice it's a little bit different than what we've been doing with regular substitution. Okay. So if you have an integrand that contains terms like this, so there's three substitutions we're going to take a look at here. The first one is if you have an integrand that contains a term like this, if you have a squared minus x squared. So if you have an integrand that contains a term like this and none of the other methods work, you only want to try this when nothing else works. Do you guys follow? So if nothing else works, then you can try this. You can substitute for x is equal to a sine theta. Normally we go u is equal to something, correct? So this is a different substitution. We're replacing x with theta. 2, if you have an integral that contains a squared plus x squared, then the substitution we're going to make is x is equal to a tangent theta. And then the last one is when you have x squared minus a squared, then we make a substitution x is equal to a secant theta. So depending upon what your integral contains, those are the substitutions we want to make to solve those integrals. Everybody okay? And I'll show you how this works. It actually is really slick, and it opens up all kinds of interesting problems we can do now once we know this method. This is a very nice method. So let's say if I give you an integral like this, we have integral of x over square root of 9 minus x squared dx. Now if you look at this problem and see, okay, you have to go through all the steps that all the other methods that I've given you. Is it a known integral? Can I do term by term? Is it a composite function? It is, right? The inside is what? 9 minus x squared. And if you were to substitute for the composite function, what's the derivative of 9 minus x squared? They'll drop that x on the top, so would that work? Would be a really good substitution here, won't it? So it would work. Now, but this integral also contains this, right? That's exactly what we have here, right? Instead of a squared, we have 9. So we can make this substitution and also do this problem, which would be an overkill here. In this case, the regular substitution will give you the answer much faster. Okay? But let's make the problem a little bit more complicated. So let's go ahead and throw in a cube here. Now, can I use regular substitution? No. So in this case, I do need to try this trig substitution because the regular substitution is not going to work. So let's go ahead and do that. So I'm going to substitute for x is equal to what? If you look at the substitutions I gave you, this looks a lot like the first one, right? A squared minus x squared. So a is what here? 3. So x is equal to 3 sine theta. So that's a substitution we're going to make. Everybody understand that? A is 3. Then, remember, anytime you make a substitution, our goal is what? When you did the u substitution, get rid of every occurrence of x, right? We want to do the same thing. But some of these are easy to replace, so let's do that. So we get I x cubed, so we get 27 sine cubed x, sine cubed theta, divided by square root of 9 minus 9 sine squared theta. So that's good so far, but then I'll end up with what, dx. But can I have dx here? Remember, substitution means what? Everything, all the x's should change, right? So what should I have instead of dx here? D theta. So I need to switch that too. So let's figure out how to do that. So out here, I'm just going to find the differential. So I get dx is equal to, you take the derivative and then you multiply it by d theta. That's how you find the differential, correct? What's the derivative of this? 3 cosine theta. Okay, so you can come out here and replace the dx with 3 cosine theta d theta. Pretty good? So let's clean up this mess, and you might look at this integral and say, okay, that was that wasn't as complicated as what I have here, right? But you'll notice in a little bit, this will clean up quite a bit, the second integral. So let's clean it up. So I have 27 sine cube theta. I'm going to take a 9 out of this radical. What will happen if I take a 9 out of this radical? Once you take it out of the radical, square root of 9 is what? So that'll become a 3, right? And then what will you be left with? Let me show you some steps here for this one time. So I have this. So I can write it as 9 times 1 minus sine squared theta. Isn't that right? And square root of 9 is what? 3. And what is 1 minus sine squared theta? What's another way to write 1 minus sine squared theta? That'll give us what? 3 cosine theta. Is that okay? So all of that just boils down to this in the denominator. And then I have 3 cosine theta on the top, d theta. The cosine thetas will cancel. So you can see that problem really reduced to quite a bit. And this is exactly the problem you did in the last section. So now we're starting to combine techniques here. And you'll see the rest of the way now you'll be combining on multiple techniques in the same integration problem. So we started with trig substitution. Now we're going to look at products of sines and cosine. So how do we do that problem? We rewrite it as what? In this case, since the exponent is odd, we break it into what? Even and 1. And then write the even exponent as what? 1 minus and then do a u substitution for what? You guys all keeping up? When I do a u substitution for cosine, what do I get? Negative sign, that'll drop that sign on the top. So we'll end up with negative 27 times theta, 1 is theta, minus, I'm sorry, not theta. This should be what? U, correct? We did a u substitution. Okay. So integral of 1 is just u. Integral of u squared is what? U cubed over 3. Change it back to theta. Look okay? So let's just take a step back and take a look at it. So far what we've done, x squared. Okay, so we did a trig substitution over here. And we changed everything to thetas. And we cleaned this up. And this is something you'll do all the time. So you can do it really quick in your head now. Because you can see what's going to happen to that radical. There's one step that I did illegally here. Which would be that this should really give you absolute values. But remember, just so you guys know, I should preface this step over here. Out here we are going to assume that theta is in the first quadrant, so it's between 0 and 2 pi. If it's in the first quadrant, x sines and cosines and tangents and everything are what in the first quadrant? They're all positive. So do I really need those absolute values then? Does that make sense? You guys follow? So we're going to assume that theta is between 0 and 90 degrees. So that's all in the first quadrant. So that's what we get. So we did that. So we ended up with this integral, cubic, and that required us to do a trig product technique, you know, and we did that. Then along the way we also had to do a substitution, so we used 3 different methods here now, right? And we get to this answer. What's wrong with this answer? We need to change it to x, but how do I change it to x now? You guys see the problem? Okay. I need to change it to x, and so to change it to x, we're going to do something we did in chapter 8. We're going to draw a triangle. So this is theta. We started with the substitution what? X was what? 3 sine theta, correct? That's the substitution we started with. So what is sine theta then? X over 3. In a right triangle, what is sine? Opposite over hypotenuse, correct? So opposite is what here? X, hypotenuse is 3. So what is the adjacent side then? Using the Pythagorean theorem, that would be the adjacent side. Everybody follow that? So now that I have that, I can use the right triangle to find my final answer. So I get negative 27. What is cosine theta going to be? Adjacent over hypotenuse, so it will be square root of 9 minus x squared over 3 minus cosine cube theta, which would be again adjacent over the hypotenuse, so it will be square root of 9 minus x squared cubed divided by 81 plus c. So you use the right triangle to change it back to x. So that's what you need to do for all of these trig substitution problems. You need to create that right triangle at the end to change it back to x. Okay. So we cubed that cosine term. Cosine cubed is just this thing. We cubed it. So cube of 3 is 27, and there was already a 3 in the bottom, so that became 81 then. Okay. That's how that 81 came up. And that's how we do these problems. They're all exactly the same. Once you understand this one, the rest of them are the same. It's just a matter of understanding when you need to use this technique. Any questions? These problems will get long because somewhere along the way you're going to have to use the products of sines and cosines. That's why we did that section before. Okay, so just keep that in mind because you're going to change it to sines and cosines or tangents and secants or something, you know. So you're going to end up with trig substitutions. Trig products, sorry. So let's take a look at another example. So I did a one for sine. Let's do one with tangents. So let's say I have, let's do square root. I have square root of 4 plus x squared over x squared dx. Let's just do x dx. Again, just to get you started, none of the techniques that we've done so far are going to work. So as soon as we recognize that, we look at the integral. Well, this looks like a squared plus x squared or something like that, right? So we can try a trig substitution. As soon as you have an integrand that looks like that, we can do a trig substitution. What is it going to be? X is what now? It's going to be 2 tangent theta because a is 2. By the way, what would have happened if this was a 5? It'll be square root of 5 then. Do you guys follow? It's not going to change that much, but I'll leave it as 4. Is that okay? So it's just a matter of swapping them. Alright, so let's go ahead and do this. So I'll come back here and substitute. So I get square root of 4 plus 4 tangent squared theta over 2 tangent theta. And then we have to change dx too, right? So we need to find the differential on the side. So let's do that. So what is dx then? It's going to be the derivative of this times d theta. What's the derivative of tangent? So we get 2 secant squared theta d theta for my dx. Now I'm hoping by now you realize why we are making these substitutions. Like out here, the reason why we made this particular substitution is what? What happened to the radical? It cleaned up quite a bit, didn't it? Because the trig identity. And why did we make this substitution? Because this radical will clean up too. And again, you can see that on the side. I have square root of 4 plus 4. I'm only going to do these for the first 3 problems. The rest you can do in your head. But we get what? 1 plus tangent squared. That's why we made that substitution. What is 1 plus tangent squared? So we get secant squared theta. So we get 2 secant theta. We'll get absolute value, but again, we're in the first quadrant. Do you guys understand that? Because we're going to use right triangle, so eventually we want the angle to be between 0 and 90. So we're good. So this radical on the top simplifies to this. So this will cancel. One of the two, the other two can pop out. So we get secant cube theta over tangent theta d theta. So how do I do this? If you substitute for tangent, you'll get secant squared. That'll drop 2 of those, but we'll still have a secant left though, right? That's probably what I would do, just to see where we get with it. So let's do that. So I'll give you a second to do that. Is that what we get? And that's, again, it's not going to help us at this stage. In section 9.6, there's a technique we can use for this when we have sines and cosines. Do you guys follow? That was in the numerator, then would be like the previous section, then we could do it. Okay, but this is not in the numerator, so that causes problems. It was a good try though. I mean, you have to try stuff. Do you guys follow? If you cannot see that, we need to try things that work. But that would have been the way to go. Hopefully things would cancel, or one of the terms would be on the top and you can do a simple u substitution or something, you know. That would be the thing. So that doesn't work because that's not going to get us anywhere. Is that okay? So what else can we do? Well, I can still work with this and see if I can make any progress here. Secant cube can be written as what? Secant squared times secant, right? Is that okay? And secant squared is what? Is that better? Anybody follow what I did? What did I do? I wrote that secant cubed as what? Secant squared times secant, and then I replaced that secant squared plus 1 plus tangent squared. We are almost done now. How can I finish this? I can distribute and split up the numerator. You guys follow? I'm going to distribute and split up the numerator, so I get secant theta over tangent theta plus tangent theta secant theta. Just think about it. Make sure you guys follow all the steps I'm doing. I'm distributing the secant and then splitting up the numerator. And you should recognize both of those integrals. Those are known integrals. So let's start with the first one. The first one is not yet known, but we can figure it out. What is it? Because now if you change this first one to sines and cosines, what do we get? We get 1 over cosine over sine over cosine. The cosines will cancel, so you get 1 over sine, which is really what? Cosecant and cosecant theta. We have an integral for that, don't we? So we can rewrite this as cosecant theta so now you can tell me each one, because we are done. We do know both of these. What is the integral of cosecant? Cosecant theta plus cotangent theta. What is the integral of tangent secant? Derivative of what is secant tangent? So this was an interesting problem. The integral we ended up with wasn't easy to do. We tried changing it to sines and cosines. We weren't able to do that, but using a little bit of trig, we were able to easily do that then. Is that okay? So just think, keep working at it. Don't give up on it just because one track doesn't work. Go back and try to look at it differently. We have to rewrite it because there's no other way to integrate that. Is that okay? And so we use trig identities to rewrite it. We are not done yet because we need to change the thetas back to x, and to do that, what do? We do the right. So if you do the right triangle, we started with this substitution: x is equal to 2 tangent theta. So tangent theta is equal to x over 2. Is that right? So let's draw a triangle. Tangent, in terms of a right triangle, what is tangent? Opposite over adjacent, so that's x and 2, and then the hypotenuse becomes what? 4 plus x squared then. So you can come out here and you can start pushing everything in. We get 2 ln of cosecant theta. What is cosecant theta? Adjacent over, hypotenuse over opposite. Okay, so what do we get? Cotangent would be what? Adjacent over opposite. Plus secant is what? Hypotenuse over adjacent. So you okay? So I showed you an example of sine. We did one of tangent. Let's do one of secant. This one I'm actually going to show you how all the formulas we did a while back work. This technically is a known integral. What is this the integral of? Secant inverse. We already know that, correct? But let's say we forgot that, but we do know trig substitution, so I can do that. Okay, so if we don't know that this is, if you did not recognize this as a known integral, then none of the techniques we've done so far will work then. So we can try trig substitution. So let's go ahead and do that. So if I do trig substitution, this is x squared minus a squared. So my substitution is x is equal to secant theta. So that's a substitution we're going to start with. So we get I is 1 over x is secant theta, times the square root of secant squared theta minus 1 times dx. So let's find the differential. Dx is equal to secant theta tangent theta, because derivative of secant is that, times d theta. So we get secant theta tangent theta d theta. Now, what is this radical going to simplify to? What's the integral of secant? What is the identity? Secant squared theta minus 1. What is that equal to? Tangent squared, and that just gives you tangent again. So that radical just cleans up nicely. So we get 1 over secant theta, tangent theta, and on the top we have secant theta, tangent theta, d theta. So all of this will integral of 1, which is theta, right? So I only have theta. I don't have any trig functions here, do I? But we started with what substitution? We started with x is what? So what is theta then? Theta is what? Isn't that secant inverse of x if you take inverse? And isn't that what we expected to pop out? So all of those formulas that we did in chapter 8, we can derive them every single one using a trig substitution. So it's just a matter of doing the same trig substitutions. If you just have theta to find, you just need to do this. Okay. Couple notes about this before I go any further. So if your answer has something like this, cosine of 2 theta. Okay. When we do when we try to change it back, and we want to change it back to what now? X, right? But when we try to do that, when we do the triangle business, there's only theta, there's no 2 theta there. So the first thing you'll have to do is use an identity and change the 2 theta back to regular theta. So you can rewrite it as what? You have a couple choices for cosine of 2 theta, don't we? So you can write it as anything you want. I'll write it as this, cosine squared theta minus sine squared theta. And then you can change that to x using the triangle. So the problem I'm saying is if you have double angles, change them to single angles before using triangles. So let me write that down. Change double angles to single angles using trig identities before using triangle, right triangle, to change back to x. So if you end up with double angles or something like that, you do need to change them to single angles because the right triangle only works with single angles. So you do need to do that. So that's one thing to remember. The second thing to remember is if your answer has something like this, ln, like if you notice out here, we had an answer like this with ln's, right? Okay, so let's just say I have something similar except I have something like this. So in this case, what we want to do is we can rewrite this how? This is the same thing as this. What did I do? Why is this the same? So why is that the same over there? Because over here, technically, if you were to rewrite, this would be over 2, right? Common denominator. Then you can use log properties and write it as what? Minus ln of 2 plus c, right? And then you can combine these constants then? Everybody follow? So if your denominator of the log terms are numbers, you always want to get rid of those denominators by rewriting them using log properties and combining the constants. So if you do that, then this is what your answer should end up being. So if your answer ends up being that, then use log properties to combine those constants. Everybody understand that? So make sure you guys do that so your answers look a little bit cleaner than what we want. Out here I could not do that because out here the denominators were what? X. I could not, it wouldn't serve any purpose doing that. Is that okay? But if you have constants, you definitely want to combine them and write them as, get rid of those denominators, and like I did here. Okay. So those are the two things to remember. Other than that, it's just a matter of grinding through these problems. Okay. So let's take a look at a few more. So let's say if I have x squared over square root of x squared plus minus 16 dx. So I'll let you do this one on your own for a little bit. None of the techniques that we've talked about secant cubed. I've told you enough times by now you need to memorize that integral because that shows up in a If you haven't done that, please do that because you're going to keep seeing this integral again and again. Is that right so far? And then remember what I said, these log terms have the same denominator, so we can combine those, right? Like we did that with numbers. So that way you can clean this mess up a little bit. So you should end up with 8 ln of x plus this plus x times the square root of x squared minus c. Yes? Because you had to square that, so you had 4 squared. Be okay with that? And that's what I meant by combining these guys, you know, the log terms, so you can clean up the answer a little bit. Here's another one you guys can do. Is that right so far? If you don't follow something, please let me know so I can explain it. But make sure you understand the algebra. It's just algebra here. I did the radical simplification for the first 3 problems on the site, but I figured by now you should be able to tell what's going to happen, okay? There's no need to keep rehashing that again and again. And this fancy integral can be written as what? Right? How do I integrate this? You can mentally go through the steps I've given you, and somewhere along the way you should be able to find the answer for this. Anybody know how to do this one? Yeah, you just use an identity in it. We're just rewriting it because we have an identity for tangent squared, which is secant squared minus 1. Secant squared is a derivative of tangent, so that's a known integral. And then just do the right triangle to finish it. So we know that x sine theta was x over 2. Sine is opposite over hypotenuse. So this is 4 minus x squared. So tangent theta would be what then? Opposite over adjacent, right? And what is theta going to be then? Sine inverse, right? If sine theta is that, then theta is sine inverse of x over 2. And there's your answer. You could also do this one. Let's say if I gave you this problem. 1 over x squared minus a squared dx. Is this a known integral? It is. We should know this. But let's say we don't know this. Do you guys follow? It is a known integral, but we don't know this. So what do? Trig substitution. Do you guys follow? Okay, so let's start with the trig substitution. So we get x is equal to a secant theta. So we get dx is equal to a secant theta tangent theta d theta. So we get I is 1 over x squared minus a squared. So you replace that, so you'll get a squared tangent squared theta in the bottom. This time remember we don't have a radical. Everybody follow that? That squares are not going to go away. On the top we get a secant theta tangent theta d theta. The a's will cancel and one of the tangents will cancel, so you should get 1 over a, the integral secant theta over tangent theta. So how do I integrate this now? So this is just basic substitution. If you've understood the last 5 problems, that's all we're rehashing again. So we have, and earlier we came across something similar. We had secant squared over tangent. Do you guys remember that? Tangent squared or something like that. And one of the things we tried initially was changing it to sine sun, which is perfectly fine. Exactly what's going to work here, because you'll get 1 over cosine over sine over cosine. These will cancel, so you'll end up with so what's the integral of cosecant theta in the front cover of the book? I want to see if you guys get that right this time. You should have it in the front cover of your textbook. There's a couple different variations of cosecant theta integral. What do we get? And the reason why I made you guys look up, because when I asked you earlier, you guys gave me the wrong cosecant cotangent integral. You guys gave me with a plus sign. Do you guys follow? If you want to go that route, then you'll need a minus on the outside, so it's easier to change that to a negative. Okay, so make sure you guys follow. That wasn't the right integral. That's why I asked you again this time what it was. So that's what we end up with. So let's do the right triangle. This is theta. We had secant was x over a. So secant is what? Hypotenuse over adjacent. So we get x over a. So this is square root of x squared minus a squared. Bless you. So we get 1 over a ln of cosecant. Cosecant would be hypotenuse over opposite minus cotangent would be what? Adjacent over the opposite. Right? And we get 1 over a. We can technically combine these because they are the same. Denominators. Good? So you could end up with this. And you can clean that up a little bit more using rationalizing and things like that, pulling exponents out. This is one of the hyperbolic inverse integrals. Do you guys follow? Hyperbolic tan inverse is what it is. Okay, so keep that in mind. Okay. You should be able to do all the homework from your that I've assigned you here. I'll just do one last problem here really quick. That last problem was the hyperbolic tan inverse. Okay, so just keep that in mind. This is x is equal to 6 tangent theta. I'm going to do this really fast just because of time, but you guys can follow. So we get 6 secant squared theta d theta over 6 tangent theta times 6 secant squared theta. Do secant squared theta as well. Oops, this should not be a secant squared. I'm sorry. This should just be secant. So one of these secants will cancel. And then you're back to 1 over 6 integral of cosecant theta d theta. And you can finish that then. You guys follow? You should be able to do all the homework from that section. It's a good section to do your homework. It'll reinforce some of the earlier sections. Okay. So just do the homework that's assigned from that section on the homework sheet. Okay. All right.